Today I am going to discuss about integrals. Although the name is world of integrals, I should say it's a fascinating world of integrals. We all of us have some idea about integration theory or the integrals. Usually by integrals or the integrals that we know is the most common thing which is known as Riemann integral. Now the question is whether we can do something more or we can extend the concept of the standard integral or which is known as the Riemann integral that we really know to something which is nothing but a generalization of these Riemann integrals, or can we use the distribution functions that we have already learned in this world of integrals, or can we define some integration theory or can we propose some integration theory based on these distribution functions. So, that would be the subject matter of today's talk. So, the world of integrals, or rather fascinating world of integrals, starts with the famous and the good old Riemann integral. Let us consider one interval, say a to b, which is a closed interval on the real line R. Now, we define a partition. By partition we mean we consider some ordered points or numbers that lies between a and b, starting with a equals to say x naught, which is less than equals to x 1, which is less than equals to, and so on to less than equals to x n, and where x n equals to b. Let us first consider that g x be a bounded real valued function defined on a b. Now, there might be some other properties of g x, but right now let us consider only the bounded real valued function that is defined on this interval a b. Now, to each of these intervals we arbitrarily select points which is xi 1, xi 2, xi n, and form the sum which is denoted by S r, r stands for Riemann integral, equals to sum over I equals to 1 to n g of xi I into xi minus xi minus 1. That means, we are considering the value of g at this arbitrary points xi I and multiply this with the sub intervals which is denoted by xi minus xi minus 1. This is the sub interval, or rather ith sub interval, and take the sum of this entire quantity. Now, since this is a sum and we can arbitrarily change the value of n rather than, that means we can arbitrarily consider the large number of points within the interval a b. That means, we can define and refine a partition of a b by inserting more points. So, this n can vary or n can go up to infinity, n might be a very large number. So, if this limit of S r, if it exists, is called Riemann integral, that means limit of S r as n goes to infinity, which is nothing but limit of n goes to infinity sum over g of xi I into xi minus xi minus 1, and we denote this thing by integral a to b g x dx. Usually this thing is usually known to us. We all know that this is nice form of the standard integrals that we have considered always. So, this type of integral, the way it is defined as nothing but the limiting sum of the functions multiplied by the length of the sub intervals and sum over all such sub intervals, and the number of sub intervals should be extremely large or it goes to infinity, and if this limit exists, then we say that this is nothing but the integral, Riemann integral, or integral of g x with respect to x within the interval a to b. Now, the question is, once I get these two things, actually there are three things, one is g x, another is dx, another is this limit a to b. Is it possible to extend or to define some general form of general definition or provide general definition of integral, at least generalizing one of these three things? And the first move in this direction is known as Riemann-Stieltjes integral. Let capital F x be a distribution function and g x be a continuous function in the interval a b, and let us consider the same partition P of this interval a b. In each of this interval, exactly in the same way as in the case of Riemann integral, in each of these intervals we define, or we rather arbitrarily select points xi 1, xi 2, xi n and form the sum as summation I equals to 1 to n g of xi I into capital F of x I minus capital F of x I minus 1. Initially, it was just x I minus x I minus 1, which is nothing but the length of ith subinterval. Now, here we are using the notion of length in a different sense, but notion of length is still there, but length with respect to measured with respect to this distribution function, and take the sum I equals to 1 to n. Now, we define Riemann-Stieltjes integral as the limit of this sum as n goes to infinity, obviously if limit exists. So, if this limit exists, then that is limit of n goes to infinity is R s, which is limit of this sum defined with respect to distribution function and is denoted by a to b g x d of f x. Now, this notion comes quite naturally from the Riemann integral, because here initially we have the length of subinterval as x I minus x I minus 1. So, that is why we have written dx, and here this is f of x I minus f of x I minus 1, hence we are writing d of f x, as if this is the change in this variable x with respect to or using this distribution function capital F. So, this is known as Riemann-Stieltjes integral. It is clear. So, let us consider one small example, where we will show that one can convert Riemann-Stieltjes to Riemann or switch over Riemann-Stieltjes to Riemann under some conditions, obviously. So, let us first consider this integral 0 to 10 x d f x, which is 0 to 10 x, and I call f x, capital F x, as a distribution function of an exponential random variable, which is 1 minus e to the power minus x. Now, little bit of manipulation gives us the value of 0.99959. Now, it is clear that this part is nothing but the Riemann-Stieltjes integral, whereas under some conditions of this property of this distribution function, or that is 1 minus e to the power minus x, we can write it as the Riemann integral of the function x into e to the power minus x. That means, this is the Riemann-Stieltjes integral of the function small x with respect to capital F x, that is with respect to 1 minus e to the power minus x, which is same as Riemann integral of x into e to the power minus x with respect to x. So, I will show you graphically and numerically that these two integrals are equal. So, this gives us the Riemann integral. So, this is the x axis and this is the plot of small f x. Small f x is x, that is x into e to the power minus x. So, this is the Riemann integral with respect to x. So, this is the area under this integral, and this is the Riemann-Stieltjes integral. Here we are integrating x, which is nothing but g x in this case, and with respect to capital F x, that means this axis we plot as capital F x. So, naturally capital F of x lies between 0 and 1. So, you see the range is 0 to 1, and this is the curve of g x with respect to this capital F x. Note that although g x is just x, but this x is plotted where the horizontal axis is given as 1 minus e to the power minus x. That is why this curved nature comes, and the area under this integral is nothing but this integral or this integral, and it is seen that these two areas are same. So, this gives us a pictorial idea about the Riemann integral and as well as the Riemann-Stieltjes integral, which is g x with respect to capital F x. Now, note that if capital F x equals to small x, then Riemann-Stieltjes integral is becoming just simply Riemann integral, which is quite obvious. We can look at this Riemann-Stieltjes integral in a slightly different way. For a bounded measurable function, may not be continuous, not necessarily continuous actually, and for the partition P such that maximum of the length of subintervals goes to 0 as n goes to infinity. That means, this partition becomes denser and denser, the points become denser and denser as n goes to infinity. And if capital M I is the supremum of g x within the ith subinterval, and small m I is the infimum of g x within this ith subinterval, then we can define capital Z as sum over this supremum capital M I into f x I minus f of x I minus 1, and we denote this by upper Darboux sum. Similarly, we can define the lower Darboux sum, and we say the Riemann-Stieltjes integral of g x with respect to capital F x exists if these two limits are equal, which is independent of any partition that we consider, provided that n goes to infinity and that maximum of the ith subinterval length goes to 0. And in this case, the common limiting value is denoted by the previous notation, integration g x d f x over a to b, and known as Riemann-Stieltjes integral. Some few notes, like Riemann-Stieltjes integral denoted by R s integral exists if g x is continuous on a b. Riemann-Stieltjes integral exists even when g x is bounded within a b and has at most a finite number of discontinuity points, provided that capital F x is continuous in every such discontinuity points with respect to g x. G x is a monotonic function, capital F x is continuous a b, then also R s integral exists. And one immediate extension of Riemann-Stieltjes integral is nothing but Lebesgue-Stieltjes integral, which is defined over any general set S and with respect to a probability measure. So, here again, like the upper Darboux sum, we define capital Z equals to summation m I into P of S I. This S I really forms a partition of the entire set S. Similarly, we can define the lower sum, where S I is a partition of S and m I and small m I are the upper and lower bounds of g x on S I. Then we can define this Lebesgue-Stieltjes integral as the limit of this sum if it exists and if it equals, if they are equal. Some few notes, like Riemann-Stieltjes integral denoted by R s integral exists if g x is continuous on a b. Riemann-Stieltjes integral exists even when g x is bounded within a b and has at most a finite number of discontinuity points, provided that capital F x is continuous in every such discontinuity points with respect to g x. G x is a monotonic function, capital F x is continuous a b, then also R s integral exists. And one immediate extension of Riemann-Stieltjes integral is nothing but Lebesgue-Stieltjes integral, which is defined over any general set S and with respect to a probability measure. So, here again, like the upper Darboux sum, we define capital Z equals to summation m I into P of S I. This S I really forms a partition of the entire set S. Similarly, we can define the lower sum, where S I is a partition of S and m I and small m I are the upper and lower bounds of g x on S I. Then we can define this Lebesgue-Stieltjes integral as the limit of this sum if it exists and if it equals, if they are equal. Till now, we started from Riemann integral to Riemann-Stieltjes integral and to Lebesgue-Stieltjes integral. While moving along these integrals, I have mentioned one thing, that we can generalize the first Riemann integral, which is integration a to b g x into d x, in different forms, and we have seen that what happens if we replace dx by dfx, which is nothing but Riemann-Stieltjes integral. And again considering a general set, we have extended this to Lebesgue-Stieltjes integral. Now, the question is, here in the especially in the Riemann-Stieltjes integral, we have not done anything with the limits, that is limit of integration, which is a to b. Now, the question is it possible to extend this limit? That means, is it possible to extend this limit to infinity? That means, can I take a as minus infinity and b as infinity? The answer is fortunately again yes, which is nothing but the extension of Riemann-Stieltjes integral. So, it can be extended to infinite intervals, but there is an important condition that g x must be integrable over a b with respect to capital F of x, which is nothing but the distribution function with respect to which we are going to define this extension of Riemann-Stieltjes integral. So, let us first consider this sum, the standard Riemann-Stieltjes sum, which is g of xi I f of x I minus f of x I minus 1, sum over I goes to 1 to n and the limit n goes to infinity, and we assume that the limit exists, then we can say that this limit equals to integration minus infinity to infinity g x into d f x whenever maximum of this subintervals goes to 0 and n goes to infinity and a goes to minus infinity and b goes to infinity. So, under some conditions, whenever we take a or whenever we let a to go towards minus infinity and let b to go towards infinity, we can think that this as an integral provided this limit exists, taking all these limits. That means, when n goes to infinity, a goes to minus infinity and b goes to infinity. So, if this exists, then we say that this is extension of a Riemann-Stieltjes integral over the extension is being made with respect to the interval of integration. So, from Riemann integral, or rather from Riemann-Stieltjes integral, we can get a generalized version of Riemann-Stieltjes integral, which is nothing but covers the entire real line. If such a function is defined over entire real line, that is g x with respect to f x, it is integrable for every interval a b, for every a and b in the real line. So far, this topic is mostly dedicated only to the definitions and not much result is associated with it still now. So, we have started to we have introduced first Riemann integral, the way we know it, and we just make some emphasis on the actual definition, or rather how we define Riemann integral. From there, we went on to extend Riemann integral to what is known as Riemann-Stieltjes integral. Now, again the extension is in terms of the variable with respect to which we are integrating. We can think of this extension in several ways. So, one such way is Riemann-Stieltjes integral, and it is defined in terms of distribution functions, at least for the moment. One can go and extend this entire thing to define Lebesgue-Stieltjes integral also. So, one important question that we can ask, what is the use of defining all these integrals? So, we will discuss this later, not now. Right now, we are only concerned with the different concepts, different notions of integrals, and how one can get one integral from other, or how one can extend one integral to the other integral, other types of integral. The use of this different definitions or defining different types of integral will come later in the subsequent talks.